Welcome back to Agastya Software Technologies Theory of Computation courses. We are discussing Theory of Computation Prerequisites Part 2. So we already discussed sets in the Part 1 and functions and relations. This is what we went through in the prerequisites part 1. In the part 2, we are going to elaborate in the graphs. We covered in part 1 also the sets. Now we are going to cover graphs. In the graphs, what is an edge, also called vertices, also called nodes. Either different terminology, either we can go called edge, node, or vertices. And what is a directed graph, directed edge? What is an undirected edge? What is a labeled node or unlabeled node? Then what is a subgraph and connected components, paths and cycles? And in the case of directed graph, what is in degree and out degree, binary relation and trees, and we are going to discuss about DAG. In mathematical way, what is a graph? When we use graph, the simple answer is when we have a group of objects, or collection of objects interconnected, then if you have that situation, to represent the interconnected objects in the mathematical way, the answer is a graph. So the graph is nothing but is used to represent a collection of interconnected objects. Now we can see here these are interconnected objects. This is one object, 2, 3, 4, 5, 6. To represent these interconnected objects, we are using graph. So this is called node. These are nodes. Node. This is node, and node, and node. Also called vertices. This is called edge. Edge or a link. Now, in the case of what is a directed path and undirected path. Now, if we have two nodes, node A and node B, if you want to represent only the path from A to B, from A to B, if you have this situation, then you go for directed edge. In the case of directed edge, A is called origin and B is called destination. Only we can travel from A to B, but we can't travel from B to A. So that is called a directed edge. So we are going to represent AB like this. Only we are going to travel from A to B, not B to A. Now in the case of undirected edge, now we will see A and B, the node A and the node B connected by undirected. When it is connected undirected means We can travel from here to here, or we can travel from here to here. If we start the journey from here, then this is origin, then this is destination. If we start from here, then this is origin, then this is a destination. Means there is a path from A to B, there is a path A to B, and again there is a path also B to A, the same path. Means we can traverse by using this path. It's not two paths, it's one path. We can traverse from here to here by using this, or we can traverse. For understanding purpose, I put two edges like this, but it is one edge. So in the case of undirected path, origin and destinations are not fixed. This is very important. Here, origin and destination, in the case of directed, they are fixed. Now, based on the edges in the graph, so we are two edges we discussed, direct edge and undirected edge. If the graph contains only, it can't contain the mixture of direct and indirect. Either all are directed or all are, this is very important, all are directed or all are undirected. If this graph contains all directed edges, then this is called digraph or directed graph. If all edges are undirected, then this is called undirected graph. In the mathematical way, how we represent the graph G equal to V and E, we are going to follow, whereas V is nothing but represents the nodes and E represents edges. So we use the notation graph G equal to V and E. This is the way we represent. Now in the case of more on undirected graph, in this one the first point is no more than one edge is allowed between two nodes. So what does it mean? Now we are here. Now if we connect like this, only one edge. We can't put one more edge because this itself represents either you can go from here to here or here to here. So we can't put the edges like this, two edges. So means the maximum allowed, the edges between two nodes is one. Only one edge is allowed in the case of undirected graph. And again we may allow an edge from a node to itself called self loop depending on the situation. Means when we want to represent node like this, here only one edge, we can do like this. This is called self loop. It is allowed. But between these two nodes, this is the node 1, node 2, node 3. Between node 1 and 2, maximum allowed edges are only 1. It doesn't make any sense if we add one more edge, because if we add like this, there is no meaning, because this edge itself can use it to go from 1 to 2 or 2 to 1 because it's undirected edge. And self loop. Next one, if we see in a graph when we use the nodes I and J, the pair I and J represents the edge that connects I and J. This is important. The order of I and J doesn't matter in undirected graph. So the pair Ij or Ji represents the same. So if this is the I, this is the J, or 1 and 2. When we use 1 and 2 or 2 to 1, means both are representing the same edge. So the order does not important. Either you can represent this edge with this pair 1 2, or you can represent with this pair 2 1. The order doesn't make any difference. Now we can see this example, undirected graph. As we discussed, between these two edges, any two edges, only maximum allowed edges are 1. Now you can see this is the only 1, 1, 1, 1. Now when we represent GVE, and V represents the nodes, so you can see the nodes. These are nodes, means node 1, 2, like in total 8 nodes are vertices. And the edges, when we see E is edges, now we can see when we are writing E equal to, when we are writing here, now when we represent this edge can be represented either V1, V2, this is used V1, E2, or you can go for V2, V1. The order doesn't matter. That is the reason we used a set notation here. In the set, if you write a set 1, 2, or if you write a set 2, 1, both are the same sets. The order is not matter in the case of set. So that is the reason these edges in the undirected graph are used, represented by a set. V1, V2 or V2, V1. So you can see the set notation here. So in total, 11 edges are 11 links. So that is the reason. So why, if the order is not important, instead of just using V1, V2, so if we use the set notation, the order doesn't important. Instead of, if we have sequence, like if we use sequence like this, the order is matters. But if we just set, the order doesn't matter. So that is the reason that the edges in the undirected graph. So this is one edge, another edge, another edge. So if you see here, they used the set notation. Set notation means order doesn't matter. So in the case of the labeled undirected graph, if we see this one is labeled, these nodes are labeled, and edges also labeled. So in the case of this one is called labeled undirected graph. Subgraph. Let's see, we do have two graphs here, graph H and graph G. Now we can note this one as node 1 and 2 and 3. This is a 4 and 5 and 6. When we note the graph H equal to GV, so this one V and E, vertices and edges. In the case of V, we can say V1, V2 to V6. In the case of edges, equal to, then V1 to V2, V2 to V3, like that we are defining the edges. In the case of graph H, in the case of graph G, and which is V and E, for this graph G, what is V? V is nothing but which is in a solid lines. So this is the graph of G. This is the graph of G. This is the graph of G, means which one? V1, V3, V5, and V6. So whenever we say graph H and graph G, when we say graph G is subgraph of graph H, the vertices of graph G, is the subset, the set of vertices of graph G. This is we can for convenience purpose we can say V1, E1 and V and V. So this is the V1. So the vertices of graph G is the subset of vertices of graph H. So means V1 is subset of V. This V1 is related to graph G and V is related to graph H. That is the first one. So the nodes are the vertices of graph G, the subset of the nodes of H. That is the first point. The second point, whenever if there is an edge between two vertices, for example V1, V2, if there is an edge in the graph G, there need to be a corresponding edge in the graph H as well, corresponding nodes. The same like this, if there is an entry V1, V2 in the E1, in the edges of graph G, definitely there need to be an entry in the H as well. That's what this meaning is. The edges of G are the edges of H on the corresponding nodes. That is very important. The nodes need to be the subset. The edges of G is nothing but the edges of H on the corresponding nodes. Then only we can say the graph G is subgraph of graph H. So the whole graph is graph H, which is indicated in these solid lines. This way and this way is graph G. So then we say it is a subgraph. The example for the undirected graph is the social network, which is the Facebook. We can see how the accounts are connected. Different accounts are connected. If there is a connection like this, we can't say connection as a unidirectional. It is a bidirectional, undirected graph. So if there is a connection between Ben and Vaidehi, doesn't mean only the connection from here to here. No, is also connection from here to here. Means the Facebook is represented by using undirected graph. The same like Sam and Aditi. If there is if it travels from here to here or from here to here. Now we are going to discuss about what is a path. What is a path? We can see a path in a graph is a sequence of nodes connected by the edges. Sequence of nodes connected by edges. So if this is the node 1, node 2 and node 3. So sequence of edges connected by a path, connected by edges. So this is a path. This is a path. What is a simple path? Does not repeat any nodes. For example, now if V4, then this is a path. If we are doing like this, then if we connect a path V1, the path is represented by the nodes like V3 and V4, and we can say if we can say this is V5 and V1 and V5. So if we take this path from V1 to V2, V2 to V3, V3 to V4, V4 to V1, V1 to V5. This path is not a simple path because there is a repetition of V1. If there is no repetition, we can say only the path from V1 to V2, V3 to V4. This path is a simple path. Here there is no repetition. If there is no repetition in the path, then that is called a simple path. If there is a repetition, then there is not a simple path. Then when we say a graph is connected, now when we say a graph is denoted by vertices and edges, you take any two nodes, V1, V2 belongs to V. If you take any two nodes, there need to be an edge between those two nodes. Means there need to be a path. There need to be a path. Instead of saying edge, we can say there need to be a path. Not the edge, the path is the right terminology. So for every two nodes belongs to V, if there is a path exists between these two nodes, then the graph is called connected graph. Next one is when we say a path is a cycle. If a path starts, for example, V1, V2, V3, V4 and V1, it is starting and ending with the same node, then this path is called a cycle. Next one is a simple cycle. A simple cycle is the one that contains at least three nodes and repeats only first and last nodes. Then this is called simple cycle. So this is what? Path, simple path, no repetition, connected for every two nodes, there exists a path, and starts and ends with the same node, any path cycle. A simple cycle is the one that contains at least three nodes and repeats only first and last node. Now a graph. Now we discussed the path, simple path. We discussed what is a path, and we discussed what is a simple path, and cycle, and a simple cycle. Now we are going to discuss a tree. When we call a graph as a tree is a tree if it is connected. What does it meaning of connected? For every two edges belongs to graph, there need to be a path. Then the graph is connected. Connected and has no simple cycles. If the graph is connected and no simple cycles, then that graph is called a tree. And again, a tree may contain a specially designated node that is called the root. And again, the nodes of degree 1 in a tree other than the root are called leaves of the tree. What is the meaning of, first of all, before we go into this point, what is the degree? For example, if this node here, if this node is connecting to only one node, then the degree of this node is 1. If it is connected to 2, then the degree of this node, so V1, V2, V3, then the degree of V1 means how many nodes it is connected? 2 nodes. So the degree of this one is 2. The degree of this one is only 1. The degree of this one is only 1. Again, if it is connected to one more, like V4, then the degree becomes 3. So now come to this point, the nodes of degree 1 in a tree other than the root. If any node exists in a tree with a degree 1, then those nodes are called leaves. So for example, if we take here, the degree of this one is 1, degree of this one is 1, and the degree of this one is 2, 3. And degree of this one is 1, 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 degree of this one is 1. So these are leaves, you can say these are leaves of the tree. Means other than the root, if any node is having degree 1, then that is called a leaves, and this is the root of the tree. Now we can say here a path in a graph. So if we take this is one path, okay, then what is a cycle? So cycle is like this. If we go on here, and this is a tree. So far we discussed undirected graphs. Let's discuss digraphs. So in the undirected graph means if the edges are undirected edges, then that is undirected graph. If the edges are directed edges, then is called directed graph or digraph. You can see here. Now V1 to V2, V2 to V3, and V1 to V2 means the edges are V1, V2, and V1, V3, and V2 and V3, like this. So here previously in undirected graph we used the convention to represent a set V1, V2 because the order is not important. Either we can write V1 slash V2 or V2 or V1, but here we use it as a sequence. In the sequence, we denote it as a sequence. So in the sequence, the order is important. If we write a sequence V1, V2, this is not same as the sequence V2, V1. So that is the reason we used a sequence to represent the edges in the directed graph. We used the sets to represent the edges in the undirected graph. So this is a very important point. So in the case of vertices V1, V2, V3 and edges is we use to represent the sequence. So these edges are ordered pairs, so which is nothing but a sequence. So the order matters, the direction matters. If you write V2, V1, the meaning completely changes. So that is the reason we use the sequence notation, and in the case of undirected graph we use the set notation. In the case of undirected graph we represented a degree. When we say degree here, in the case of undirected graph, how many edges it is connected means it is 2. But in the case of directed, now we have two type of degrees, out degree and in degree. Now we can say node 1, the number of edges going out from here 1 and coming in 2 means out degree is 1 and in degree is 2. So in how many coming in degree, how many going out degree. So this is what out degree and in degree in the case of digraph, but in the case of undirected graph only the degree, we can't say out or in degree. Now in the case of undirected graph only we consider as a path, we say as a path in the case of undirected graph, but in the case of directed graph we say directed path. Directed path. What is the meaning of directed path? A path in which all the arrow points in the same direction as its steps is called a directed path. So for example, you can say here the directed path is, so from V1 to V2, this direction, we have to go in the same direction from here to here, then this is one path. So one path is V1 to V2 and V4. Only in the same direction, this is one path. We can say another path from here, then V1 to V5, V5 to V6, and V6 to V1. This path is a cycle, but before going to cycle, we then we can say V1 to V5, V5 to V4. This is a path in the same direction. So now comes to this one. That is what directed path. You can go either only one direction, either this way or this way. Means all the arrows need to point in the same direction. A directed graph is strongly connected if the directed path connects every two nodes. So if we take any two nodes, V1, V2 belongs to V, if there is a directed path between these two elements, then the directed graph is called a strongly connected graph. That is the second one. Next one, a directed graphs are handy way of depicting binary relation. We will elaborate more this one later. So these are very handy way if you want to define the binary relation. If R is a binary relation whose domain you can see is D and D, then we can label that one G equal to DE represents R, where the edges we can say X comma Y, X or X. So we will elaborate on this more in the upcoming sessions. Previously we used Facebook social media to represent undirected graphs. Facebook. Because in the Facebook, if there is a connection between Sham and Vaidehi, then definitely there is a connection between Vaidehi to Sham. This is obvious. So there is no need to, there is not a unidirectional. It is an undirected graph. But in the case of Twitter, it is not an undirected graph. It is a directed graph. If somebody is following, for example, Jeff is following Vaidehi, it doesn't mean Vaidehi is following Jeff. So now in the case of Vaidehi is following Nick, again if Nick is following Vaidehi, then there is a two arrows like this. So the Twitter is the best example for digraph, and the Facebook is the example for undirected graph. What is a DAG? A directed acyclic graph. DAG is a directed graph. Directed graph means the edges are directed edges, and without cycles connecting to other edges. So a directed graph without cycles connecting to other edges is called DAG, a directed acyclic graph. Now, how we will represent a directed graph by using a binary relation. For example, if you have a binary relation on set A is subset of A cross A, Cartesian product, then now this is set A, B, C, D, E, 5 elements. Then we're going to have a relation which is a subset of A cross A, R is subset of A cross A. Then we are defining R as this relation. So this relation is going to be represented as a directed graph. Now there is now we are representing in the directed graph as a sequence, as a tuple. In the case of undirected graph, we use like this notation. In the case of directed graph, we use this notation. Now there is a edge from A to B. A to B, there is a directed edge, and B to C, there is a directed edge, B to C, and again E to C, then there is an edge E to C, a directed edge, and D to A from D to a directed edge, and D to D, a self loop. So this is what we discussed in the case of here. If R is a binary relation whose domain is D and D, labeled with the G equal to DE, then R is going to be represented as, means we can use a directed graph, or we can use a binary relation to represent a directed graph. This is a special case of binary relation, is also called a directed graph. Now we are going to elaborate. This is the very important to understand strings and languages. What is a string? What is a language? How to represent the strings? So the topics we are going to cover: the alphabet. Now this is the Greek symbol we used to use. This one, sigma, is an alphabet. And what is an alphabet? We are going to discuss a set of symbols. Set of symbols like this is any symbols we can use like that, 1, 2, 3, any set of symbols. Always finite set. This is very important. We'll discuss this one. Always finite set of symbols. Then what is a string? String is a finite sequence of symbols. Now we can see this is a string and this is a string. Finite sequence of symbols over an alphabet. Now if we take an alphabet 1, 2, 3, this is a string over this alphabet. And if we take alphabet as A, B, C, D and E, then the string is A, B, D, E and D, A. So this is a string over this alphabet, means finite sequence of symbols. Then epsilon, empty string, epsilon, empty string. Now what is the length of the string? Now we can take this length of the string. Now how many symbols? 1, 2, 3, 4, 5, 6. This is the 6. Now in the case of here, 1, 2, 3, 4, 5, 6, 7, then 7. Then epsilon is an empty string. The length of epsilon is 0. Then we are going to elaborate concatenating. When we have two strings, X and Y, then what is the concatenation operation we are going to discuss. Then if you have a string, the reversal of string, X power R. Now you can example here, X is Anju, we can say, and Y is Bika. Now we can say concatenation XY means the string X followed by Y. Then it becomes Anju Bika. Then we can say YX, then it becomes Bika Anju. So this is what concatenation. So concatenation is not symmetric. XY is not equal to YX. Is not symmetric. This is very important. Then reverse is like this. If X equal to BAC, reverse is CAB. This is what the reversal of string. Then what is a string? Now when we discussing what is a string, a string of characters these are the very fundamental building blocks in the computer science. Sequence of characters. So string means sequence of characters. Now when we are defining an alphabet, when we are defining a string, first we need to have an alphabet. So strings always, this is very important, strings always defined over an alphabet, only one alphabet. So the alphabet over which the strings are defined may vary with the application. So whenever you have an alphabet, you can define a string over that alphabet. Now, when we define an alphabet, you can see this is an alphabet. These are called members of the alphabet. 0 and 1 are members of this alphabet. These are the members of this alphabet. And also we use two Greek symbols, then sigma, and also like this, these two Greek symbols we will use to denote alphabets. So these are the alphabets of this one. These are symbols of this alphabet. So alphabet set of symbols always finite. So this is very important. And again we have to remember the strings cannot be defined over two alphabets. No, you have to take either these or this, not two. Now here the string over an alphabet is a finite sequence of symbols from that alphabet. This is important. When we have an alphabet AB, the string over this one is a finite sequence of symbols. Like for example, A, B, A, B, B, A, A, B. So this is a finite sequence of symbols over this alphabet. This is one string. Next is, this is a string. Now we can see this is an alphabet, then this is a string over this alphabet. This is important. Now we can see this is the string over this alphabet. This is very important. When you define a string over which alphabet, this is very important. Next is if W is a string over alphabet sigma, then the length of the string is the number of symbols in that string. Then epsilon is empty string, the length of epsilon is 0. The empty string plays the role of 0, means in the number system. Epsilon is, the length of epsilon is 0. Now we can see the string, empty string is epsilon. Epsilon, the length is 0. Then this is a string, length is 7. Then if you have this one, if we can write of length, if the W is the length, we can write W equal to W1, W2, W3, where each WI belongs to the alphabet sigma. So the reverse of W equal to some A, B, A, B, B. Then the reverse of that one, so B, B, A, B, A, the reverse of that string. So the reverse of that one is written as W power R, is a string obtained by writing the W in the opposite direction. Next, the string Z is a substring of W if Z appears consecutively within W. What is it meaning of consecutively? If we can see this is a string, if this is a string, then this is a substring. CAD is a substring, not CDA is a substring. They need to appear consecutively. We have to take that part. If we take that part, if we divide A, B, R, A, C, A, D, A, B, R, A. Now, this is the start of this one, this is the end. You need to take consecutive starting from any alphabet, any character, either from here, here, here. If you start from here, you need to consecutively go and you have to cut. Then this becomes a substring. You can start from anywhere. From there, you need to move forward. How many characters you want, you need to take and cut it down. Then it becomes a substring, consecutives. So far we discussed strings. What is a string? String is nothing but a finite sequence of symbols over an alphabet. And again, the length of the strings we discussed. And the concatenation of two strings xy is not equal to yx means concatenation is not symmetric. And a reverse of string. And also we discussed substring and also empty string epsilon. Now we are going to elaborate more on what is a language. Language is a set of strings and empty string, and empty language is denoted by 5 empty language. This is empty language, empty string, and one more language you can see. This is a language consisting of empty string. And how to describe the strings? This is the topics we are going to elaborate by using enumeration. This is an example. Regular expressions, this is an example, and context-free grammars. These are 2 examples, and set notation. Let's discuss more on Boolean logic. This is very important to understand for our theory of computation. As we discussed all these topics so far, we discussed are the prerequisites. In the part 1, we discussed a few topics, and this is also the part 2. Now, what is a Boolean logic? In this Boolean logic, we are going to discuss the and the conjunction, or disjunction, and negation. This negation is like this, negation. Also we can use like this, and exclusive or, this one exclusive or, and equality. And the equality is denoted like this. You can use this way and this way and this way. Equality implies or implication. So you can use 1 arrow or 2 arrows, implication. So, and conjunction or disjunction, not, exclusive or, equality, and also you can use like this, and implies, implication, and distribution law. P and again C, Q, R, Q, R, R. Now this one is like this. So this is the distribution law. P and Q are P and R. Now this is a very simple. Now how it going to be? How to remember this one? The distribution law. This becomes P and Q. Now it goes to in the bracket. When we have to remember, this is very easy to remember. Now when we have P and Q R, you have to remember P and, first you have to take the Q. So P and Q, we have to close the brackets, and R, then you have to start, and P and R. P and R. This is, you have to remember like this. And in the same way, P, R, like Q and R, this one, then you have to start P, R, Q, then, and P, R, R, like this. This is the distribution law. Then De Morgan's law, not symbol. When you apply not symbol, negation of A union B, A or B, then negate of A, then and. See, R becomes and, negate of B. Or you can write negate, you can use this notation or this notation, A negate and B negate. Now in the case of same, if it is and, it becomes or, if it is or, it becomes and. The same like this. So this is the De Morgan's law. Now the Boolean means it is having only two values, true and false. True is denoted as 1, false is denoted as 0. Boolean logic in mathematical system is built around two values, true and false. These two values are called Boolean values. Also we can go for this notation, true or false notation, or 1 and 0. 1 represents true, 0 represents false. Now there are the situations: a wire that may have high or low voltage, a proposition that may be true or false, equation that may be answered true or false. These are the possibilities. But anything, the Boolean logic means anything which is gonna yield the answer true or false, that is called a Boolean logic. And again we can manipulate Boolean values with the Boolean operations. We're going to have the Boolean operations. The simplest operation is the negate. Negate means if you have a true, if you negate true, it becomes false. If you negate false, it becomes true. So this is the negate symbol. Means if you negate 0, it becomes 1. If you negate 1, it becomes 0. And again we can use conjunction. When you use conjunction here to manipulate two Booleans, if it is true and true, it becomes true. Then true and false, it becomes false. Then false and true becomes false. Then false and false becomes false. Means if they are same, it becomes like, see, if true and true, true, true and false, false, true, false and true, false, false and false, false. The conjunction of two Boolean values is 1 if both are 1. Means both are true, then it is true. In all other cases, it is false. You can see here. So whenever you use or, if both are true, true, in all other cases is a false. Then in the case of or, either see true or true, then becomes true, true or false becomes true, false or true becomes true, false or false becomes false. So any one of them true, it becomes true. So these are the two differentiations. In the case of and, if both are true, then only it is true. In all other cases, it is false. In the case of or, either of one is true, then it becomes true. If both are false, then only it is false. Means if both are false, it is false. In all other cases, true. Here both are true, it is true. In all other cases, false. Completely opposite of this one. This is what this one is, OR operation. Now we can see this is the truth table of the example. 0 means false, then false and false. The same we need to remember. So in this case of and, if both are true, if both are true, then only true. In all other cases, it is false. Here, if both are false, then only false. In all other cases, it is true. And negate, true becomes false, false becomes true. Exclusive or XOR, also denoted as XR. This is the notation. What is XR? If we see, if both are same, then the value is 0. Means either both are true or false, means false and false, then false. Both are true and true also, it becomes false. Means if both are same, then becomes false. If both are different, means any one of them is true, then it becomes true. That's what this operation is. Is 1 if either but not both of its operand is 1. If either of one operand is 1, then its value 1. Means we can put it that way as easy to remember. If both are same, then it's false. Both are different, then it's true. Or otherwise we can remember either of one is true, then it is true. If both are true, it also becomes false. Both are false, obviously false. This is what the XOR operation is. And you can see equality operation here. If both are same, it's completely different. If both are same, then it's true. Both are different, it is becoming false. Means 1 if both operations have the same value. Previously, if the both operations in the case of XOR, if both operations have the same value, it is 0. Both operations are different, it is 1. But it's completely different for the equality. If both are same, 1. If both are different, 0. This is what the equality is. And the implication, only in this case 1 followed by 0. The first operand is 1 and second operand is 0 in the case of 0. In all other cases, the value is 1. So these are XOR, equality and implications. Let's discuss the summary of what is the terminology we are going to use in our course. In the next session, we are going to start with the finite automata. So when we are starting, so this is what we are going to use the terminology: alphabet, a finite non-empty set of symbols, argument. What is an argument? Is input to a function. A binary relation, a relation whose domain is set of a pair, like this is a binary relation. Binary operation, an operation on binary values. What is a binary value? Either true or false, or 1 or 0. This is the binary value. And concatenation, a operation that joins strings together. Now we have two strings, AB, W1 and BA, then concatenation is W1, W2. This is what the concatenation is. And the conjunction is AND operation. And a connected graph, a graph with the paths connecting. You can take any two nodes if there is a path exists. Now when we have a graph of GV, you take any two nodes of V, means either V1, V2 belongs to V, any two nodes of V. If there exists a path between these two nodes, then the graph is a connected graph. Then what is a cycle? A path which starts and ends with the same node. Node are vertices. Then it is called a cycle. Then disjunction is OR, conjunction is AND. So what is a domain and a range? We discussed the set of possible inputs to a function. Now we can see here when we are mapping a function, this is called a domain, this is called a codomain, and also this is called a range. And also we discussed the edge. What is the edge? And we say G equal to VE, set of vertices and set of edges. And element, an object in a set is called element, empty set with no members. and empty string is also called epsilon, a length of 0. Also a function we discussed, an operation that translates the inputs into outputs like this. When we have a function is defined with the domain into codomain or domain into a range. And a tuple and sequence, what is a sequence? Like when we have a sequence here, finite sequence is called a tuple. In the case of k tuple is number of elements, k objects. And language, set of strings, again the alphabet, finite set of strings is an alphabet, sequence of characters is a string, a set of strings is an language, member an object in a set, node a point in a graph, ordered pair. In a sequence order matters, in the set order doesn't matter. Then the path, a sequence of nodes in a graph connected by two edges. Then the predicate, a function whose range is, so predicate means whose range is true or false, then that function is called a predicate. Property is nothing but a predicate. Again, range, a set from which the outputs of a function is drawn, range or codomain. Sequence, a list of objects. So the sequence and set, the set order is not important, order doesn't make sense, then sequence is order makes sense. So the set we use this notation, sequence we use this notation. A simple path, a path without a repetition. Singleton, a set with one member is called singleton. A string, a finite set of symbols from alphabet is a string. Symbol, a member of an alphabet. A tree, a connected graph without simple cycles. Unordered pair, a set with the two members, vertex, a point in a graph. And also we discussed the union, an operation that's combining two elements like union. And relation, what is a relation? We discussed graph. Intersection we discussed, equivalence relation we discussed, which is reflexive, symmetric and transitive, then it's called equivalence. Also discussed complement and directed graph and Cartesian products. So this is what we required, the terminology and the basic understanding before we start the theory of computation. This is what we covered part 1 and part 2. Regarding to part 3, we are going to discuss these prerequisites of part 3 before Turing missions. As part of part 3, theorems and proofs, lemmas, corollary, conjuncture, if and only if, proof by construction, proof by contradiction, proof by induction, structural induction, first order logic. All these we are going to discuss before the Turing missions. Thank you for watching. We will start our first session, finite automata, in the upcoming session. Thank you very much.